We're going to determine the equations of any asymptotes and then graph the given function. Let's start by determining the vertical asymptotes. Remember, before determining any vertical asymptotes, we do want to see if the numerator and denominator have any common factors. But x squared plus 3 does not factor, so we will have a vertical asymptote at the 0 of the denominator. So the vertical asymptote will occur where x minus 1 is equal to 0, so the equation for the vertical asymptote will be x equals 1. So let's go ahead and sketch that. Here it is. Now to determine if the function has a horizontal asymptote, we'll determine the limit as x approaches infinity of the function. Now there's a shortcut method for determining this limit. If the degree of the numerator is greater than the degree of the denominator, this limit is going to approach positive infinity and not exist. We can see that since x squared is in the numerator is growing faster than the denominator, and therefore this is going to approach positive infinity, which means there is no horizontal asymptote. However, since the degree of the numerator is 1 degree higher than the degree of the denominator, this function is going to have a slant or oblique asymptote. So to determine the slant asymptote, we have to perform this division. So let's go ahead and do that on the next page. So we'll write this quotient as a long division problem. So our dividend is going to be x squared. We'll have a 0 term for x, and our divisor is x minus 1. So by performing this division, we'll be able to determine the equation of the slant asymptote. So x times x will give us x squared. So now we'll determine this product. We'll have x squared minus x, but we need to subtract, but instead we'll add the opposites. So we'll change this to addition, change this to a negative, and change this to plus. So this is actually going to be a positive x. You bring down the next term, that's plus 3. What times x would give us x? That'll be positive 1. So now we'll multiply 1 times x minus 1. That's going to be x minus 1. But again, we're subtracting this quantity, but instead we'll add the opposite. So we change this to addition, change that to a negative, change that to a plus sign, and the remainder is 4. So what we've discovered is that f of x is equal to x plus 1 plus a remainder of 4 all over x minus 1. So now looking at this function, notice as x approaches positive infinity, this quotient here is approaching 0, which means the function will be approaching the line y equals x plus 1. So our slant asymptote is the line y equals x plus 1. Let's go ahead and graph this on our coordinate plane. So we have a y-intercept of positive 1, and we also have a slope of 1, or 1 over 1. So we'll go up 1, right 1, up 1, right 1, and our slant asymptote is going to pass through these points. So it might look something like this. And now we need to find some additional points on our graph by completing a t-table. So we do want to pick some convenient values for x. Let's try x equals 0. If x is 0, notice how our numerator would be 3, our denominator would be negative 1, so y would be negative 3. This would actually be our y-intercept. Now let's try x equals 2 as well. If x is 2, we'd have 2 squared plus 3, that's 7, all over 1, so that's 7. Let's go back and plot these 2 points on our function. We have 0, negative 3, and 2, 7. 0, negative 3 is here, and 2, 7 is here. Let's try selecting 2 more values. Let's try x equals 3 and x equals negative 1. If x is 3, we would have 9 plus 3, that's 12, divided by 2, that's 6. And if x is negative 1, we would have 4 all over negative 2, which is negative 2. So let's plot the point 3, 6 and the point negative 1, negative 2. So again, we had 3, 6 here, and -1, -2 is here. And that should be enough information to make a nice graph because again, we know it's going to pass through these points and then approach the vertical and slant asymptote. So it might look something like this for this piece, and this piece might look something like this. So here's a decent graph of our given function and the equations of the vertical and slant asymptotes.